welcome to today's class. Today I'm going to continue speaking about the hyperboloid and about its group of Riemannian isometries. So recall that last class we introduced Minkowski's form on R3 by as kind of very similar to the usual dot product, except that it has a minus when one pairs the third coordinates. So it's plus, plus, minus. And then we introduced the hyperboloid by looking at the level set of the value -1 of the quadratic form associated to Minkowski's form. And then seeing that this level set has two connected components, right? It's a two-sheeted hyperboloid. And we defined the hyperboloid model, or just simply the hyperboloid, as the upper sheet of this two-sheeted set. And we saw that Minkowski's form itself is makes this upper sheet of the level set of -1 a Riemannian manifold. Right? So on each tangent plane of the hyperboloid, so for the tangent space of the hyperboloid at any point, Minkowski's form itself gives you an inner product. So M, it's a Riemannian manifold, and that's what we saw. And then we said that this class we were going to speak about the group of isometries of the hyperboloid. So okay, so the first thing what I'm going to do is I'm going to look at a certain matrix Lie group and study this matrix Lie group. And the first thing I want to argue is why look at this matrix Lie group. So I want to motivate the discussion by looking at the Euclidean plane. So for the Euclidean plane, when we look at its isometry group, well, we see that there are certain isometries that are linear transformations of let's say R-linear transformations, and namely, for instance, rotations. Right? Rotations around the origin are linear, and also reflections with respect to lines that pass through the origin. Those are linear as well. Right? But there are many isometries that are not linear. Right? For instance, when you rotate around a point different from the origin, you have a non-linear isometry, for example. Reflections with respect to lines that do not pass through the origin are also not linear, right? And also, for example, translations, right? Translations, those are not linear, right? And so let's focus a little bit in translations, right? So every non-trivial translation, right? So every translation by a non-zero vector is non-linear, right? So translations are somehow non-trivial translations, right? So translations different from the identity are the prototypes of non-linear functions and actually non-linear isometries of C, right? Here C, let's say with its usual norm, right? That can be seen to come from let's say the usual dot product or the usual Hermitian product on C. So okay, so they are not linear, and then one asks, okay, so is there a way of kind of realizing them as linear transformations of some space, right? And the answer, well, we saw already the answer, right? That is by looking at a C square and thinking of C as sitting inside C square at height 1, right? So when we introduced the complex projective line, that's when we did this. Then we saw that translations of C are somehow like hide one shadows of certain linear maps, right? Namely, maps from C squared to C squared, so of a space of a higher dimension, given by these ones, right? And then later on, then we interpreted this, it's kind of the parabolic modus transformations that fix the infinity. Okay, anyway, so my point is, so by looking at height one, by looking at the space in whose isometries we are interested in as height one, as a certain subspace, a certain topological subspace, or certain affine subspace, or certain surface, let's say, in a space of higher dimension, then we can interpret the translations of our original space as coming from linear maps of the space of higher dimension. Advantages of this, well, for instance, one thing is, for instance, here it is kind of quite transparent that that translations form a matrix Lie group, for instance. So whenever we need some result from Lie groups, then we can appeal to that fact, for instance. Let's do this more systematically. So let's define the Euclidean group. So it's kind of the level 2 Euclidean group, let's say, or the Euclidean group for dimension 2. Of course, it's not that the group has dimension 2, but that the space has real dimension 2. And then let's define it to be, the group of isometries of the Euclidean plane. Okay, right, and then inside this group, there lie, for instance, these translations, right? The translations that we just discussed, and then adopting this philosophy from realizing translations as linear maps of a space of higher dimension, we find that actually the Euclidean group is isomorphic to certain subgroup of the orthogonal of O3, of the orthogonal group of R3, of the three-dimensional real space. So Euclidean space. So this one, remember that it's all the 3x3 matrices whose columns are pairwise orthogonal, or whose basis, more correctly, whose columns form an orthonormal basis of R3. So in particular, the elements here, they always have a determinant 1 or minus 1. Okay. Anyway, so you see, by placing R2 in the space we are interested in the space in whose isometries we are interested in, at level 1 in R3, we see that every isometry, well, first of all, it's quite easy to see that every isometry of R2 can be written as a composition of first an isometry that fixes the origin, and then a translation, right? So doing something around the origin and then translating. So if we do something around the origin and then translate, but at height 1, this way we realize the Euclidean group as a subgroup of O3, as a closed subgroup actually, right? Because I mean these are actually closed conditions. So we see that this one is naturally a matrix Lie group. Okay, I'm going to leave it as an exercise. I pretty much already told you what to do, right? I mean, show that every isometry of R2 can be decomposed as a composition of two transformations. The first one of which is an isometry that fixes the origin, and the second one of which is a translation. Okay, and like once you show this, which is a fact which is pretty easy to show, then the isomorphism is really immediate. And another exercise is that actually this subgroup of O3 actually coincides with the subgroup of O3 that preserves bijectively R2 placed at height 1. Okay. All right. So this preliminary concerning Euclidean isometries, well, it gives me a hint of something of what to do for the hyperboloid, because it tells me, okay, if trying to follow the same philosophy, if you want to study the isometries of M, then okay, then how about looking at some space of higher dimension on which M sits naturally, and trying to realize or to locate some group of linear transformations of this space of higher dimensions that induce isometries of the hyperboloid of M, of the hyperboloid, and then you see, once you locate that group, then try to see if you can obtain all isometries of M this way. And of course, we produced the hyperboloid as sitting naturally in certain space of higher dimension, right? Namely the Minkowski's space, namely R3 with the Minkowski's form, and a group that comes immediately to mind is O3, right? I mean the group of sorry, not O3. Sorry, not O3. The group that preserves the bilinear, that preserves the Minkowski's form, right? Namely, if one defines this matrix, right? I mean, if one takes the matrix of Minkowski's form with respect to the standard basis, then look at all invertible linear maps of R3 that preserve this form. Okay, this group, which we are going to denote O21. So this is why I got the confusion. It's O21, not O3. O21 because 2 plus signs and 1 minus sign in the form. This we're going to denote O21, and it's commonly known as the Lorentz group, terminology coming from special relativity. And of course, at some point we are going to also speak about the special Lorentz, the proper Lorentz group. So SO21, which is frequently known as the proper Lorentz group, special relativity, which is the elements of O21 that have determinant 1. Now, notice this. Every element of the Lorentz group has determinant 1 or minus 1, and this just comes from this identity, right? I mean, just take determinants, and then use the fact that the determinant of the transpose is equal to the original determinant, and then you obtain this. Because the determinant of J is obviously minus 1, so you obtain the determinant of A squared is equal to 1. So the determinant of A has to be plus or minus 1. Okay, So which means that that the proper Lorentz group is kind of is a big subgroup of the Lorentz group, right? It's actually half of the Lorentz group, right? It has index 2 in the Lorentz group. So in particular, for instance, as Lie groups, they have the same dimension. This one and this one have the same dimension, right? The first thing one is tempted to say is that this one is the subgroup of this one, is the connected component of this one containing the identity. That's not quite true, and then we will see this later on in the class. Okay, and then just as we did with SL2R and then with SU11, is to characterize those matrices, those invertible matrices that actually belong to O21 in terms of the action on their action, in this case in Minkowski's space. Right? So so the conditions are that for an invertible 3×3 matrix with real entries belonging to the Lorentz group is equivalent to the following 4 conditions. First, that it preserves the Minkowski's form at all points, right, for all V and W. Second, that it preserves the quadratic form, which is kind of a priori. This is kind of a special case of this one when V and W are equal. Right? So somehow this condition is kind of a priori more general than this one. Okay, then you see this condition tells me that you see that if V is in the inverse image of certain value, then a V is as well with respect to the quadratic form, right? Inverse image with respect to the quadratic form. So this condition, that A preserves every inverse image. You see, and here I'm not putting bijectively, right? Just sends every pre-image into itself, and right. So this condition actually is kind of a shadow of this condition. And the next condition, okay, but sorry, but this we require. You see, condition 3. Yes, it's a shadow of condition 2, but only for 3 very special values of C. So while 2 tells me that this happens for all C in the real numbers, condition 3 tells me, okay, you only need to look at these 3 special values. Condition 4 tells me that actually if this happens, you actually have equality for these values. And of course, all of this is equivalent, as we said, to the matrix being inside O21. Okay, about the proof. So first, let's focus on 1 if and only if 2. So 1 implies 2, as we said, it's obvious. And 2 implies 1 comes from the polarization identity, right? I mean, namely the fact that you can put this symmetric bilinear form in terms of its associated quadratic form. And then you apply this polarization identity and, well, use the fact that multiplying by A is linear. So here this sum opens. Okay, so 2 implies 1, less obvious, but once we remember the polarization identity, it's quite straightforward. Okay, 1 if and only if 4, right? 1 if and only if 4. Well, 1 implies 4 is obvious because these are you see, the entries here are precisely the values of Minkowski's form at the pairs of standard basis elements, right? I mean, this is how we took J, to be precisely, so that its entries, you see, its ij entry is the value of this value. Sorry, it's ej. So 1 implies 4 is obvious. So it's here, yeah. Right. And 4 implies 1. It follows from the fact that if knowing this means knowing this, which means knowing this for the standard basis vectors. But then if you apply the linearity of A, and you see like for any vector, for any two vectors VW, you expand, and then you expand in terms of the standard basis, and then for each pair of standard basis vectors, you apply this equality that you know to hold, and then you arrive at what you want. So 5 implies 1. Sorry, I had said 4. It's 5. It's quite obvious. So we know we have 1 if and only if 2, and 1 if and only if 5. Okay, now let's go with 2 if and only if 3. 2 implies 3, as we said, is obvious, right? Because this condition is a particular case of this condition for when one looks at inverse images of these elements instead of inverse images of arbitrary real numbers C. Right? So 2 implies 3 is obvious, and 3 implies 2. Well, 3 implies 2, we use the fact that you see that the quadratic form is homogeneous of degree 2, and so for every real number and any vector, it's kind of square linear, if you will. So one has this identity, and of course A was always linear, right? So if we take this value, you see, if Q of B is C, then well, this one, right? Q of this one is, because of this, equal to right. So this one the square comes out, so it's 1 over the absolute value. But Q of B was C, right? So this guy is in 1 minus 1. So okay, if you are going to tell me, okay, if C is 0, so give me a moment. When this is not 0, then we can then applying this hypothesis. You see, when something gives you 1 or minus 1, A of it does it too. So this one is equal to Q of A of this guy. Okay, and by linearity we can put this one here, right? And then we apply again that this equality, so we obtain this. Okay, and then from this being equal to this, we see that we can cancel this, and then we obtain Q of AB is equal to C as well. Okay, and now for C equal to 0, well, for C equal to 0, if you see, if we are using this, right, then it's obvious, right? That you see, it's part of the hypothesis. So, okay, I mean, this case, the case this equal to 0 was already covered in the hypothesis, so that's why I didn't consider it. Okay, so we have now 1 if and only if 2 if and only if 3, and 1 if and all of this equivalent to 5. So only the equivalence to 4 is remains to prove. Okay, so assuming 2, which is something here I should have, assuming 2, right? So that Q of AV is equal to QV. Well, from that, what we deduce is that for all real numbers, A of the inverse image is contained in the inverse image. Now, A is bijective, right? I mean, multiplying by A is a bijective function. So everything here is A of something. Okay, that that something cannot be in a different Q inverse of L, because then this would land in Q inverse of L. And this would land here. But this one and this one are disjoint. So the thing I took here, it's A of something, and the something must be here. So one actually has equality. Okay. And then 4 implies 2. Well, 4 implies 2, so you see 4 obviously implies 3, and we already saw that 3 implies 2. So done, and that's it, right? So that finishes this characterization of the elements of O(1). So those that preserve the form, those that preserve the quadratic form, preserve inverse images of the quadratic form, and preserving them is always preserves them bijectively. Okay. And now, as a corollary of this proposition that we just proved, if I take an element of O(1), then in particular, you see when we apply 4 for -1, we see that A of M belongs to Q inverse of -1, right? So A of M has to be plus or minus 1 by continuity, right? By continuity of multiplying by A, because Q inverse of -1 has two connected components, right? Namely the upper sheet and the lower sheet. The upper sheet is our, so the fact that multiplying by A is a self-homeomorphism of R3 means that then A, being in O(1), either preserves M bijectively or exchanges the two sheets. And the other sheet is minus M, precisely. Okay, so somehow this means that we have, that actually by looking, this is a good candidate, right? That we hit a good candidate. Okay, but that maybe we have to consider only those elements of O(1)R that actually preserve this one. Right? So that maybe not the whole group is to be considered, but a subgroup. Okay, so now you see here in this result that we just proved. Here you see this is 4 is really strong, right? I mean, it's really strong in the sense that to preserve all pre-images, which is 2, which is condition 2. It suffices to check this, right? To check only for -1, 0, and 1. Okay, so somehow, how about you see by looking only at the hyperboloid, and the two-sheeted hyperboloid, right? So can it be true that a matrix belongs to O(1) if and only if it preserves the inverse image of -1, so that one doesn't need to check 0 or 1, but only one needs to check only the inverse image of -1? And can this be, sort of weakened or kind of apparently weakened by an argument similar to the argument with which I proved 2 implies 4, so that one only needs to check this condition. So I leave it as an exercise. I don't find it so easy to solve, at least not at this point. So I think this is a good exercise, a challenging exercise. I think. Okay, so some terminology and some nomenclature. So I already hinted here that maybe we don't have to look at the whole group, at the whole O21, but at the subgroup of those A's that actually preserve M. We're going to do that, and that is called the orthochronous Lorentz group. Here I'm following the terminology of that I think physicists use in special relativity, and then also I think some physicists use this plus sign here. I'm going to change it because it confuses me a bit. I'm going to tell you where it confuses me. So I'm going to use, instead of O plus, I'm going to use M. So that to recall that it's the elements of O21 that preserve M. So this is the orthochronous Lorentz group, and then from them, so you see here, think about, for instance, reflection along the XZ plane. You see that reflection along the XZ plane. It's easy to check that it belongs to the orthochronous group, to O21, right? So it obviously preserves the upper sheet, and one checks easily that it also preserves Minkowski's form, but it has determinant -1, right? So that's kind of the source of the confusion, that some elements here can have -1, can have determinant -1, and the plus that was here, the thing is, it refers not to the determinant, but to the fact that it sends AM to plus M. Right? Okay, and similarly, for instance, consider the rotation around the x-axis. Rotate the 180 degrees rotation along the x-axis. That one has determinant 1 and sends M into -M, right? So it has determinant +1, but it does not belong to O plus, O21 plus, right? So, okay, so to avoid that confusion, to avoid those possible confusions, then I prefer to just replace with an M. Okay, now, from those elements here, we take the ones that have determinant 1, and then we call it the proper orthochronous Lorentz group, or simply the restricted Lorentz group. So to give you a hint of what's going to happen, which is a non-trivial fact. So the theorem is going to be that the orthochronous Lorentz group is the full group of Riemannian isometries of M, and the restricted Lorentz group is going to happen to be the group of isometries of Riemannian isometries of M that preserve the orientation. Okay, so that's kind of a hint of what's going to happen. Then next thing. So this is a useful observation. So in order for an element, in SO21R, so namely, you see here it was defined the proper Lorentz group. So not the restricted, but the proper. Right? So the ones that have determinant 1, have determinant 1, but they can still exchange the two copies. Not the two copies, sorry, the two sheets. Well, you know, a continuity argument, a topological argument, shows that in order to preserve M bijectively, it's enough to exhibit one point whose image under A is in M. Okay, and then I leave it to you as an exercise. It's an easy exercise in topology, right? So to verify that, you know, when you have a matrix that you know already preserves Minkowski's form and has determinant 1, in order to preserve M, it suffices to just exhibit one point that is preserved. Okay. Now, of course, by definition, the restricted Lorentz group acts on M, right? by its very definition. Okay, and then kind of one of the first things we asked, like for instance, one of the first things we asked for modus transformations had to do with transitivity, and then well, it better be transitive, right? It better be transitive because if this is really going to be the set of isometries of M, of Riemannian isometries, and if M is actually going to be a decent Riemannian manifold, it better be transitive, because otherwise there would be like special points in M, right? Or some points where you cannot move with an isometry, etc. Right? So this action better be transitive because of what I told you is going to happen, right? And if M is actually going to be a decent Riemannian manifold. So that actually happens, and the proof is, in my opinion, very instructive. So take any point, and what I'm going to show is that given any point, there is an element in HG.03.01 plus, in the restricted Lorentz group, that takes the point 001, which is some sort of north pole of the two-sheeted hyperboloid, to my given point, right? And then everything is going to follow from the observation, right? Because then the north pole would be preserved, and then you would have this, and by definition, A of the north pole is going to be this point, and then transitivity is transitivity will follow, because then you can just send something to the north pole, and then from the north pole here. Okay, so take an arbitrary point, and then, well, that arbitrary point comes with its tangent plane, right, embedded as a vector subspace of R3, right? So take a basis of that tangent, that embedded tangent plane. So it of course has two vectors, right, because this one has dimension 2, and the two vectors live in R3. Okay. Right. So now the thing is, B is an orthonormal basis, right? We are taking an orthonormal basis. So this means that the dot product of this one with itself is 1. The dot product with this one with itself is 1. Sorry, the Minkowski, the Minkowski form of this one with itself is 1. The Minkowski form of this one with itself is 1, and the crossed ones are 0. Right. So this already tells me that with this one I already have a 3 by 2 matrix, that starts to behave like at least belonging to O to 1, right? to at least preserve Minkowski's form. Okay, but now remember also that this tangent plane is actually the Minkowski orthogonal of P. So when we add P, we at least have Minkowski orthogonality with these two. and P itself belongs to M, so the Minkowski form with itself is -1. Okay, so we're pretty much done, right? I mean, we just put everything in a matrix, and then of course we have to take its transpose and then see what this sort of transpose conjugation does to the matrix of Minkowski's form. Okay, so everything reduces to precisely what I said happens. That the columns of this matrix that you see that this one with itself gives you 1, this one with itself gives you 1, this one with itself is -1, and the crossed ones give you 0. So A is in O2, then we know that A automatically has a determinant plus or -1. Okay, maybe it's -1, right? But if it's -1, we know what to do because we know that switching columns of a matrix change the sign of the determinant. And then we just have to be careful which columns do we switch. Well, the thing is, look here, when you multiply with the vector 0, 0, 1, this product rescues the third column, right? Okay, so you don't want to move the third column of A. Okay, then you exchange these two. Okay, so if A has determinant -1, then just exchange these two. If it already has determinant 1, don't do it. So then we have an element in S21R. So in the proper Lorentz group, that takes this one to P, but then, as we said, taking this one to P suffices for preserving M. So A lives here and preserves M. So A actually lives. So maybe let me write it. By the observation, actually A belongs to SO2R. Plus, and here, sorry, here I should also say, because you see, yeah, this one refers to determinant +1, and this plus actually refers to preserving M. So let me do that as well here. Which means that here I have to write. Okay. So the action is transitive. Okay, good to know. And then this whenever one has a kind of a Lie group acting transitively in a manifold, one may be able to say something about the topology of the Lie group. Because why? Because the fact that the action is transitive implies that for any point in M, the space of left cosets of the stabilizer of the point here, the quotient this one by that stabilizer, is homeomorphic to M. So at least we know that this one modulo any stabilizer, even though that may not be a group, that quotient, because the stabilizer need not be normal. But even nevertheless, we know that this one modulo something is homeomorphic to M. So maybe we are able to say something about the topology. Okay, so let's prove a preliminary lemma in order to do that. And the lemma says that if you have a topological group and a closed subgroup, if it so happens that both the subgroup and the space of left cosets of H in G, where of course here you put the identification topology. If both of them are connected, then so is G. Okay, which here, for instance, if we are going to apply this lemma, that since we know that M is connected, then if we can show that the stabilizer of any point is connected, then we automatically can deduce that this is connected, right, from this lemma. And the proof is not very hard. The proof of this lemma is not very hard. It's more or less a standard proof in topology. So suppose we have a kind of a disconnection, so that we have two open sets that are not empty, neither of which is empty, and whose union gives you G. So okay, so I'm not assuming that U intersect V is empty, right? So from these conditions, I want to deduce that U and V must be not disjoint, right? So that U intersect V is not empty. Okay, so now from this, of course, we have that G modulo H, the space of cosets, is the union of the projections of these two, right? So P is the projection, the canonical projection from G to the space of left cosets. Okay, now these ones are open. Why? Because, for instance, consider pi of U. Pi inverse of pi of U is open in G because it is the union over all H's in H of U times H. And these ones, each of these is open because U is open and G is topological group, right? So this one is open. So these two sets are open. They are not empty, of course, because U and V were not empty. And then, okay, now since G intersect H is connected, then this means you see this, the fact that they are open and the fact that they are not empty means that the intersection must be non-empty. Right? So this means that for some G, I mean some left class, some left coset belongs here. Right? Okay, so this left coset belonging to both means that I'm sorry. First, this, of course, means that for this subset of G, the subset itself is the union of the part of the subset that belongs to U and the part of the subset that belongs to V. Right? So this is obvious from this. And now, from the fact that this one belongs to pi of U and pi of V, well, we see that we can express, you see, there is some element in U, pi of which is G. So there is some element of U that belongs to this, right? So this intersection is not empty. And similarly, there's some element of V, pi of which is this. So this means that element belongs to the class. So this intersection is also not empty. And then you see, since H is connected, this one is connected. Which means, so you see, we are expressing this, you see, this connected set as this union of these open sets of the set, because we give the relative topology to this set, of course, which are neither of which is empty. So the connectedness of this one, which follows from the connectedness of H, implies that this intersection is not empty. Right? And here it shouldn't say a contradiction because I didn't assume that U intersect V was not empty. I said that's what I want to prove actually. So maybe I can just say that hence U intersect V is in particular not empty. Sorry about that. It's an alarm that I didn't set off. I hope it doesn't come off again. Anyway, so we see that in order to prove that a topological group is connected, it is enough to exhibit as a closed subgroup which is connected and such that G modulo H is connected. Okay. Okay. Now, let's show that the restricted Lorentz group is connected. And here again, I have to write M. So I'm going to give two proofs. One proof that somehow it is useful because it can be applied in more general settings more easily, and another proof which really kind of which is very ad hoc to the fact that we are working, that we have this space of dimension, like this very specific space. Okay, so yeah, so let us write G this, right, and then the north pole of the two-sheeted hyperboloid, and then let's compute the stabilizer of N. And the stabilizer, well, for the action of G. Okay. Well, you can easily see that it's actually this one. I mean, just play around with the fact that take a matrix A such that A of this point is this point, and then you arrive at this, where the upper corner is actually an orthogonal matrix of determinant 1. Okay, and then you see this one is connected then because the special orthogonal group for R2 is isomorphic as a Lie group to the circle. So in particular, it's diffeomorphic. This exercise is quite easy. So it's connected, right, because this one is connected. And now, on the other hand, you see, since the action of G on M is continuous, the space of left cosets of these stabilizers is homeomorphic, and actually I could say diffeomorphic to M, which means that this one is connected, because it's homeomorphic to this one, which is obviously connected. So G is connected, right, by the previous lemma. Okay, alternative proof to actually give a homeomorphism with a connected set. Right? And actually, I'm going to give a homeomorphism with a solid torus. Yeah, and what I'm going to do is I'm going to give a homeomorphism between the restricted Lorentz group and the solid torus. Because you see, M is homeomorphic to R2, and R2 is homeomorphic to the disk, to the unopened disk. So this is actually a solid torus. Okay, so given a matrix, somehow I already know what to do from the argument when I showed that the action is transitive. Something I can do is look at what it does to the North Pole, right? I mean the image of the North Pole under the matrix. That's just ABC, right? Right, and then look at you see at this element of S1, and that's it, right? I mean, we know that these are orthogonal, right? And that we have determinant 1 for the whole matrix. Right? So those two facts make that somehow this determines this one. Right? So it's enough to see this point, to see which point in the unit circle of the tangent space of M at ABC determines. That's the point. And this you see this, you can see these are infinitely differentiable functions, right? I mean, this one, this. And then you check that it's bijective. Okay, so, and this one is connected. So this one is connected. Okay, now, so you remember that when we defined this one, here, sorry, again, I have to remember. Okay. So recall that here, remember that we said that it would seem that this had two connected components, namely determinant 1, determinant minus 1. That's not the case. And somehow, you see, let's say the intuition as to find, how many connected components, which here I'm saying 4. Kind of, let me give some intuition. So at least kind of, I have already determinant 1 and determinant minus 1. Okay. But determinant 1, it can exchange the two sheets of the hyperboloid. So in determinant 1, you have the component of those that preserve M seem to form a component, and those that exchange the two sheets seem to form another component, right? Because somehow, if they exchange the two sheets, you cannot go from exchanging the two sheets to preserving both sheets through an isotopy, right? Because in any or through a path, let's say to 1, because to go, you at some point you have to leave the group in order to go from one to the other. So at least that seems to be the component, and also for determinant minus 1, right? For determinant minus 1, for instance, you can say, okay, I have some elements that preserve both sheets, namely, for instance, a reflection along a plane passing through along a vertical plane passing through the origin, right? Like the XZ plane or the YZ plane. And then you can say, okay, that followed by a rotation. And again, that seems to split the set of matrices, or the subset of this one consisting of matrix of determinant minus 1 into two components. At least it seems, right? So it seems that this has at least those 4 connected components, right? So determinant 1 preserving M, determinant 1 exchanging both, determinant minus 1 preserving M, determinant minus 1 exchanging the two sheets. So that's at least some intuition as to like why this is reasonable to expect. Right, and then this one we know it's connected, and then of course it would be desirable that this is already the connected component of the identity, both here and here, so that kind of nothing in either of these groups that is connected to the identity is missing from us, right? That we haven't missed any such element. Okay, so now this one, this alternative proof is useful because since we have a diffeomorphism between this one and a three-dimensional manifold, we see that this one is three-dimensional. That the restricted Lorentz group is three-dimensional. So it's a three-dimensional Lie group. But then you see, you just check these ones, and I mean, you check their dimensions, and they are also three-dimensional Lie groups. So this I give you as an exercise to check that the dimension of this one is 3 and that the dimension of this one is 3. Right? Yeah, which I think can also be seen from what I argue here. Okay, so for C, this one is a three-dimensional Lie group connected. So it's contained in the connected component of the identity of each of these groups, and the connected component of the identity here and the connected component of the identity here, it's a three-dimensional Lie group. So this one is a three-dimensional connected Lie group contained in a three-dimensional connected Lie group. They have to be equal. So that this follows from the fact that all three groups really are three-dimensional, and the fact that this is already connected. Okay. Right, and for A and B, what you know, for the number of connected components of this one, what I do is just formalize this argument of having determinant plus minus 1 and independently being able to exchange or not the two sheets. I formalize it into a group homomorphism, which turns out to be continuous, and whose kernel is precisely the restricted Lorentz group. And that's it. I mean, you see that it's continuous because the determinant is a continuous function, right? It's a polynomial function, so it's continuous. And then you see A goes to A dot n to multiplying with the North Pole, it's continuous. Then taking the third coordinate of a vector is continuous, and taking the sign of a non-zero number is continuous. Right, and the third coordinate is never 0. The third coordinate of this one is never 0. So this one is never 0 because it's always greater or equal than 1. This is in the upper. Sorry, the absolute value is always greater or equal than 1 because this one is either in M or in minus M. So yeah, I'm taking the sign of a non-zero real number is a continuous function from R minus 0 to 1 minus 1. So you see this you explicitly see that this is continuous, that sigma is continuous. So continuous and surjective. So you have that this modulo, the kernel, is homeomorphic to this. So you are done. Okay, and here is a picture. So kind of to avoid confusion here, let me write here M. And here also M. So okay, so remember, this is the orthochronous Lorentz group. So it preserves M even if it has determinant minus 1. So having determinant 1 or minus 1, but preserves M. Right, and here we have the ones that have determinant 1, some of which may be sent M to minus M. And then here we have the other ones, the ones that have determinant -1, and exchange the two sheets of the hyperbola. Okay, now well, we have been studying these groups, right? The Lorentz group, the orthochronous Lorentz group, and the restricted Lorentz group. And of course, at some point, the theorem is going to be that this one is the whole group of Riemannian isometries. This R is for Riemann, for Riemannian. This R is for Riemannian as well. That this one is the full group of Riemannian isometries, and that this one is the full group of Riemannian isometries that preserve the orientation. So this plus is for the orientation. Okay, so you see here is where one point where having a plus here would be a possible source of confusion. And I would say that now these two inclusions, these two containments are obvious. Why? Because if you give me a matrix, you see a matrix which preserves M bijectively, well, you see its derivative as a function from R3 to R3 at any point is the matrix itself. So in other words, for any matrix, in particular for any matrix here, the derivative of multiplying by A at any point in R3 is the matrix itself. Right? So okay, and this one, you know, if you give me P in H, not in H, sorry, in M. You see, since A takes M onto M bijectively, I know that you see that A takes the Minkowski orthogonal actually into, well, it's enough to say this. We actually have equality, right? Why? Because being here, it preserves Minkowski's product, right? So if something is orthogonal to a point in M, its image is also orthogonal, right, with respect to Minkowski's form. Okay, and actually multiplying by A, you see, it's actually the derivative mapping. And inside this one, the interior product, the inner product in this space there is a restriction of Minkowski's form. Right? So for any two, well, here I already used V. Let me use U1W here. I have A U A V to 1. That's equal to U V to 1. So for any point, well, A is the derivative, and A will satisfies that, and A respects the Minkowski, the interior product or the inner product of the space. Right? And here actually one has equality, you know, by the original discussion here. That one actually has equality. Okay. So it's a Riemannian isometry. Right, and then these ones, you see that they preserve that. In particular, they preserve the orientation here. Well, it follows that that you already know that they preserve the orientation in R3. So that part I give as an exercise. Okay. Now, one would like here to have equality, right? I mean, it's a promised theorem that here we have equality. That both containments are equalities. Okay, so somehow, right now, an argument for that. An argument for that would be, for instance, take any isometry. We would like to see that this isometry is given as the restriction to M of a matrix belonging here, right? Of a linear map of a linear map acting in the bigger space R3. Okay, right. Then look at what it does at the North Pole. So okay. Suppose this one. Suppose the isometry you took doesn't come from a matrix, and take and you see so take an element here. Suppose that it does not come from a matrix, and look at what it does at the North Pole. So the image of the North Pole under that isometry, and the derivative, right? from the tangent space of the North Pole to the tangent space at the image of the North Pole, and with that information, form a matrix as we did before, right? Like as we did it here in the proof of the transitivity of the action. Okay. Now we are assuming that our isometry does not come from a matrix. So when you compose, going with the matrix and then coming back with the inverse, you obtain an isometry that fixes the North Pole, has the derivative at the North Pole is the identity, but does not come from a matrix. So if we solve, if the answer to you see, if we see that only only the identity fixes the North Pole and has the derivative, so that the identity is the only Riemannian isometry fixing the North Pole and having the derivative being the identity, then what I just said, that it would be impossible to find the isometry here that did not come from a matrix, right? And that would prove equality, right? So this would imply equality. And the exercise here is whether you can prove that now, that the identity is the only Riemannian isometry that fixes the North Pole and has the identity as derivative in the North Pole. In the North Pole only, right? I mean, we wouldn't assume anything else. In particular, you wouldn't assume that it fixes some other point or anything. Okay, and as well, we are going to see later on that this happens. And then the question is whether you can prove this now. I would say that these are right now like extremely challenging exercises. I would say that right now they are really hard to prove, and somehow actually the strategy I have to prove, well, this and that here one has equalities. The strategy I have in mind is actually going to establishing a Riemannian isometry between M and some other, and the unit disk on the hyperboloid. Actually, as I said, pull the Riemannian metric of M to the unit disk and to the upper half plane, and then in those spaces, show that one has the corresponding equality, and then put that equality here. And showing that in those spaces one actually has the desired equality is not a trivial fact, I would say. So I would say that these exercises are actually very challenging. So these are here we have to come back to showing that in these containments, in these inclusions, we actually have equalities. We are going to come back with the strategy I just said. But before that, I mean, at this point, we have to talk about hyperbolic cosine and hyperbolic sine. I mean, in general, this is the moment where the hyperbolic trigonometric functions appear in the course. So I have to make a parenthesis and speak a little bit about the trigonometry of the hyperbola, and then we will come back. Right? I mean, namely, I'm going to see how the hyperbolic sine and the hyperbolic cosine really come from a hyperbola. Right? So I'm not going to define them as in terms of the exponential or in terms of a series or so on. I'm really going to define them in terms of some arc length in the hyperbola, right? Like measuring some sort of angles in the hyperbola. Okay, so that's it for today.